Do you think you guys or anybody that has been watching my channel for a while probably know how to do ADC, but there's also a lot of professionals out there that, you know, they do the projects in a completely different way. There's so many ways to do the project in the STM32. Like, you can use the HAL, you could use the Cube MX, and you can also do it register level. And you could also use assembly language to do it as well. So who knows what ADC is? Everybody? Or let me get a number 1 in the chat if you know what ADC is and how to use ADC, or if you've ever done a project in ADC. And I guess 0 if you don't even know what ADC is. I guess I could put a poll up here. It has some hissing on it, unless I can figure out how to get this thing to work. Let me try this one more time to see if I can plug it in. It's probably going to turn my camera off, so we'll see. So this is the bare metal chip. It's just a plain chip with the breakout board connected to 3 breadboards. So that's it, and you have a programmer. So that's all we're working with, is the bare chip, the pins that are broken out to the pins of the breakout, and the breadboards. So this is the way I've been teaching microcontrollers for 17 years. Personally, I like it better than like the Arduinos, because you're not starting with a whole bunch of components on the board. And if you're doing this professionally, it's a good way to start, because you can build up from the bare chip. And it's, in my opinion, it is just as easy to use a bare chip instead of an Arduino. So, you know, I personally like it. Is okay with the sound? That's a good question. Why do you think that? Peter is saying STM32 doesn't seem super friendly for hobbyists compared to Arduino and Pi, but also ESP. Anyone also feel that? I want to know why you think that, because I mean, we could do a project together, and I can demonstrate. It's pretty easy. I've just edited a video that I was making for this one, the ADC, and it was, I mean, it's very simple. What you're doing is you're programming the microcontroller. You're flashing the microcontroller with a program that you create in C++ or C, which is the same thing you're doing in Arduino, although Arduino uses libraries, but you could also use the HAL libraries at the same time, which is very simple to use. So they're very straightforward. I think it's really just I personally think it's just the idea of working with a bare chip and not being able to plug right into a USB. That might be the worst thing. But in the case of this, you know, platform, all you have is the chip and you have the programmer, which is USB. So I'm kind of curious why you guys think there is a barrier to entry on the STM32. So let me know from you guys out there, why do you think it's more difficult for the STM32 to develop? I'm really curious about that. I think it would be, I mean, if you haven't watched my videos, maybe that could be, never used it, but I think it needs special programmer. No, it doesn't. It does need a programmer, but I mean, the programmers are cheaper than Arduinos, and you only need one. So for every project that you're going to do, this is essentially used to flash the microcontroller. But I want to take that stigma out of people's minds that it's a difficult thing to do. It's not. I mean, I'm an urban designer, and I started bare chip microcontroller programming from the start. I didn't start. You know, there's a lot of marketing out there for Arduino, and I think they sell it as being the easy way. And it's also, you know, there's so many different manufacturers marketing the shields for these boards, but you can also get discrete components and devices to work with a bare chip as well. It is a big conversation, I know that, but I mean, that's why I'm doing live streams. My intention on this live stream is to do a project with you, and you guys guide me. If there isn't anybody here that is at that level, I have no problem, you know, doing the project myself, step by step. I also have a book that shows all of the stuff that you need to do to program these microcontrollers. So if you want to get into the lower level or bare chip and then build up from that, that book is a great resource. The only parts that would be, I guess, a barrier would be the appendices. There's two appendices. One, how to flash the chip, and the other one, how to compile. So it's relatively easy for that. Certainly the Cube ID and the Nucleo boards have been a great starting point, although hit some horrible issues straight away. The Nucleo is just like the Arduino. It's very similar. You have a board that is a development board that has a bunch of components on it that in production you'll probably never need. And that's one of the things that I think is good with working with just a single chip is you're starting fresh. You determine the components that you need. You determine the programming that you make, and your cost, the production cost, can be whatever you want it to be. If you started out with an Arduino and you are wanting to do this as a production, then you would need to essentially reverse engineer what the Arduino is. You'd have to know what components are being used in your program on that board, the Arduino. I didn't really want this to be a conversation about that, but I don't want there to be an idea of this being a difficult thing. And also, I'd love to do these live streams more frequently so you guys can understand the ease of doing this. I think it's a good resource for you guys if you have any problems, and I would love to even share those projects. If you're having problems, share the same exact project in a live stream. I think that would be a really good way to help new users out, newcomers into this bare chip microcontroller platform, and it would be, beneficial. So it would be beneficial for me because I'm able to get my point across and my tutorials out there with real projects, which would be really good. All right, let's take a look at some of these comments. Because you have to buy the right programmer and download the right software correctly. The same programmer is used for all the STM32s. It's the ST-Link, not a big deal. And I think you can get them for $4 on Amazon or AliExpress. You can also get them from my website. I would love the basics and go from there. I've only worked with Arduino and Pi. I love being able to use .NET IoT Core for the Pi until Microsoft killed Windows 10 IoT. Yeah, you're not going to be using the .NET with the STM32, but I think there are some projects out there that you can. I know you can use VS Code for it, but I generally use what is recommended by STM32, which is the STM32 Cube IDE, which I can show you in this live stream if you want. Sir, I have watched many videos of you. STM32 is very friendly to those who seriously starting with MCU. Arduino is for kids to ready-made project. Yeah, one thing I want to say about that, Arduino is, I don't want to trash Arduino completely. There are some scenarios, or probably most scenarios, are people using Arduino for one-off projects. Like you want your sprinkler system to work in a certain way, or you want to make something that you're going to be using a single time, and you want to do it really quickly. Even though you could do it really quickly with a bare chip, the barrier is advertised as very low with the Arduino, and you can do that. I'm from university. Can you please share which series I should in my course to teach embedded systems, and what low-profile IDE portable so that they can carry it in pen drive through the access? I think the STM32 Cube IDE might be good. I don't know what the portability is, how small it is, but thumb drives are pretty big nowadays, so you can probably fit it. It's based on the Eclipse IDE, so I think it's relatively portable. Learning how to do bare metal is great. I would love to get into more advanced things and truly understand the makeup of how things work. Okay, cool. Well, let's see. How would you guys like to do this? Do we want to go ahead and do the ADC project, or do you want to do something simpler? What are your thoughts? There's one way to start with an Arduino with all the components and do the projects that you want to do, or start from the beginning where it's a single chip and you branch out from there and you create the circuits that you need in that circuit, and only that. I mean, the STM32 would be a good platform, or a comparable microcontroller would be a good platform to even make boards like the Arduino, or like the ESP32, or like the Pi. You know, it's that kind of thing. Right, you can just generate the HAL code, copy it without the useless bits, and pretend you wrote the bare metal code. You can do that. HAL is there for you. It's hardware abstraction layer. It's a way to create the code. Although I don't do it, I don't use HAL, and I don't even know how to use HAL. I've done it in a few of my videos. Only after doing quite a bit of research, I find that working with register level code is actually easier, and that's easier for me. But the HAL really isn't intended to be easy. It's intended to be compatible with other chips. It's intended to be compatible with all ARM chips. You are right. In Skeptic, you're right. The question is, the problem is the whole board is cheaper than the chip. You're right to a certain extent. If you're doing getting a single chip versus getting an Arduino might be cheaper. But learning in that respect may not be the best idea if you want to scale. And scaling meaning like you go and work for a company designing washing machines for LG, whatever. Because there's microcontrollers in pretty much any device you have in your house. Using an Arduino in that sense, you go up to your manager and say, well, I only know Arduino, and how do you need this project to be lean? You're not going to get a good response from your boss. I think I think there may be a misconception of what I do and my intent. My intent is for teaching anybody using the bare chip. If you bought 1,000 of them, they're going to be extremely cheap. If you bought 10,000 of them, because you're making 10,000 washing machines, they're going to be very cheap. It's just economies of scale. If you're going to work with Arduino and then the company needs to buy every single component that's on that Arduino, it's obviously not a good idea. You'd have to re-engineer everything from the beginning, and then start with a single microcontroller and then branch out. That's bottom-up thinking, I guess. And there's also the top-down thinking, probably just as good if your mind works that way. This is a good conversation. I'm loving it, actually. Okay, so CNC Time-Lapse says, I have always wanted to learn advanced things, so this is exactly the kind of knowledge I'm looking for. If you started with the basics, that's cool with me, but I'm pretty quick at picking stuff up too. Which HAL are we talking about? Linux CNC? No, we're not talking about Linux CNC. We're talking about bare chip, the HAL libraries for ARM specific. I believe, I'm not really sure because I've only worked with the STM32, so the HAL libraries for STM32, I'm not sure if they're the same for NXT or other chips, but if you're using HAL, generally you can use the same code for various chips as long as they have the same peripherals that you need to use. Peripherals meaning they have the same ADC, the same number of ADC, the same PWMs, the same outputs on some chips may not have as many outputs as other chips, like different packages, smaller packages with fewer leads on the package may not have as many, obviously it doesn't have as many pins, so it won't have as many outputs. I'll use this analogy as a programmer. If you know how to write from scratch a complex task rather than rely on a framework or library, you'll always rely on the library. Yes, that is true. In my book and my videos that I've created over the 17 years, you'll notice that when I create the code, the initialization, the actual code to make things work, I then create my own library, so it's just easier to use. So I'm only needing to write a single line of code, and the main code, if I'm going to be reusing it, I'm going to be putting that into the main file. Be as lean or perfect as maybe some engineers would be making libraries, but you can still use other libraries, but also make stuff that you need. Like if a library doesn't do what you need it to do, then just write the thing from scratch and make it work. There are enough Hopefully you can hear me. There are enough libraries out there that probably do what you need it to do, but there's enough documentation out there, like data sheets and reference manuals and things like the reference manual for the accelerometer that I was going to use in this video has a data sheet, and it shows you exactly how to make it work, what the parameters are, so you can use that in your Scratch programming to make it work. Actually, the stuff that makes this work is very simple. It's just an output voltage, and you're plugging it into a voltage source. You're powering this device, and then it's going to give you a voltage out on the acceleration. Yeah, skeptic. I know it's hobby. I'm a hobbyist. I used to sell Arduinos, by the way, a while back, just because I was using it for my 3D printers, the ones that I was. There's no need to a hobbyist shouldn't think that it's too hard to do. If they tried to do it and if they watch the right videos on how to do it, it is very, very easy. Writing C code is writing C code. You're doing it for the Arduino. You're doing it. So I wouldn't be afraid of getting into bare chip development right from the beginning, and that I think is the way to go. But that's my personal opinion. So, and if the stuff that I talk about and the stuff that I teach, if you want to learn this type of stuff for bare chip programming and bare chip development, stay here. If you still are having frustrations, come to my live streams, talk about it. If you get completely frustrated, do Arduino, or do whatever you want. It's really not of any consequence. I mean, I am a resource for you if you want to do bare chip. That's what I'm trying to say. Dask, sir, if you have time, then try to make a bare metal STM32 TM135/157 custom board with own Linux OS. I don't get into the OS stuff. I pretty much stay low level like I do. I guess an example would be my vacuum pressure or this board that I developed for an old 3D printer, which has a microcontroller on it and a driver for a stepper motor. It's for a resin printer. So I don't get into the OS side of things. I don't go as far as that yet. At least I haven't gotten into that. That's where the Raspberry Pi. If you need to go to the level of, okay, I need to add files to it, and I need to manipulate files, read files, and have some kind of operating system environment, that's not where I go. I do stuff like using the microcontroller to control stuff, like the washing machine controls the on-off, the various modes, controlling the motor. It starts the motor. Maybe it starts maybe you have the dryer and washer all in one. A single microcontroller can control all of that stuff, but it doesn't have an OS. So that's not something that I generally do. I might get into that later on if I have a need to access files. You can also access files from an SD card from microcontroller. You don't actually have to have an OS with it. Another thing is like drones. They use microcontrollers. They control stability and everything with the single microcontroller, but it doesn't require an OS to do that. That's kind of the thing I'm talking about. All right, that's what I would love to. CNC Timelapse says that's what I'd love to be able to do. Read a data sheet and understand what all that means. That's something we could do here. Is we could go over the data sheet for the TE830M1 if anybody wants to take a look at that. Know the basics electronics, but man, I couldn't tell you how to read the data sheet, and that's fine. And the data sheet tries to put everything. It really is kind of simple. It's just giving you minimums and maximums and what pins do what the typical stuff is on a pin, what it would expect, that kind of stuff, and it gives you lots of graphs. So it tells you what you could expect if you actually use and certain conditions of temperature and how temperature and other contextual parameters affect the device. Okay, Gerald Donnelly, How's it going, Gerald? When's the second volume of your book coming out? Been watching Amazon and haven't seen it. Good question. I'm still writing it. It's been slow because of having to feed my family, and business hasn't been doing very well these days. Build Your CNC is losing a lot of traction from competition and stuff, but it's not a big deal. It's not like I really need it to work out. I'm semi-retired anyway. Okay, so Skeptic, just to make it clear, I have no problem with that. I do my own boards, own libraries, can code, and have good electronic background. Don't use Arduino, just the hardware. I'm going to order your book. Where's the best place to order it? Can you put a link of your book in the description? All right, let me see here. I will put a link in the description, but I'll also show you where you can find it on my website, because I also have the kits. I kind of want this to be more of a question and answer rather than a self-promotion. But all right, so there's a link for the main. This is my advanced. If you just click on this, it's the advanced kit with the book. You can also buy the book in the website, and I don't think I have a link to the Amazon one, but if you just look up Amazon, I'll put this in the. If you just put in our microcontroller programming, you'll probably see it #1. So just click on that, and I can't put a link in the chat. Not even me. What the heck? Oh, it's too long. All right. I know how to take care of that. Unfortunately, it's going to have to be an affiliate link. Let's see if this works. Yeah. Sorry for the affiliate link. Not like I make any money on it anyway. I already get royalties from the book, so it doesn't really matter. Why do I feel bad about that? Okay, so if you want just the, let's see, let's go to ARM development here. So you can just buy the microcontroller and interface board by itself, just so you have something to work with, because this is very difficult to find. This is the LQPF package, 64-pin package. So if you went to Amazon, SMD 64-pin, I don't think you'll find anything, but if you do, you can use that as well instead of using mine. You might be able to find it in here, but I don't know if it goes up to 64 pins. This might be it right here. So you might be able to do it, but it's very difficult to get it on a breadboard if you do it this way. I've designed mine specifically for plugging into the breadboard. And I'm going to be showing a lot of videos or live streams on me using KiCad and designing stuff. I'm actually going to be making some changes to this board, and I'm going to be I'll put that on live stream so you guys can make it. You guys can make a board like this very easily on KiCad anyway, and just send it to JLC PCB or something like that, which is my sponsor. Definitely go over there. It'll be in my other video. Given a thermistor, this is from Robert Lugg. Hi, Robert. How do I read the voltage and output in it? A thermistor works like a resistor, and you could use it as a voltage. I'd have to look at that. So let me take a look at that. Maybe on another stream, I can show you exactly how to use it. But it's just you're looking at a voltage difference between a voltage divider. I'd have to look at the thermistor and how it works, and look at that data sheet as well. Thanks, CNC. Dask, sir, do you have any bare metal project with STM32 and a camera module? Not yet. That may be a little bit advanced for me, but I'll check that out. Are you referring to maybe doing some machine learning stuff with it, like face detection and things like that, or what specifically do you want to do with the camera module, or just show video from the camera? You'd have to have with the STM32 controller that I'm using right now, probably can't handle it because it's I think it's maximum 16 megahertz, or I can't remember. I have to look. So the speed isn't really there for processing the camera feed. Okay, so motion detection. Yeah, you might be able to do that, but you'd want to select probably a higher Cortex number chip for that. I haven't gotten into that yet, so I apologize for that. But yeah. Hey, I'll be back. How's it going? All right, so CNC said he wanted to look at a data sheet. So I'll show you the data sheet for the 2000G accelerometer. It's by TE. They're a little bit expensive because of the high the high G rating of them. All right, welcome, I'll be back. Thanks for coming by. All right, so this is what a data sheet looks like for this particular device. And generally the first page will have information on what it does, the features of it, and what it contains. So this one is, I don't know if this one is the, yeah, this one is the 25G version, but it'll show, generally it shows the other versions and what model numbers it has. But this is the, I usually just go straight here to look at the pin configuration, and it has a pin number and the definitions of the pins. These three here and these three here are not connected. See 4, 5, 6, 10, 11, 12 are not connected. And you have the 9 is the power, and 7 is ground. 8 is a built-in sensor for temperature. It's an accelerometer, but it includes a temperature sensor as well if you want to use it. And the 1, 2, 3 right here is X, Y, and Z out. These are just pure voltages out. So generally the data sheet's going to talk about the characteristics of these pins. It also talks about the dimensions of the package, like in this one right here. And ask questions, by the way, as I'm going on, so I can answer you. And if this is a little bit out of your league, just let me know. And I don't really, I mean, I've been doing this for 17 years, but still, I sometimes have some problems with looking at data sheets. So here are the different versions. They come in plus or minus 25 to plus or minus 2000. The one that I have is 2000. The most advanced thing I've done with an STM32 is really I've just done the projects on the website, on the videos. This project here is Atmel. It's not STM, and I have a whole series of Atmel videos as well. So whatever I can do with the Atmel, I can pretty much do with the STM32. They're pretty much the same. I'm probably going to trigger some people here, but working with an AVR microcontroller and working with an STM microcontroller, if you're working with register level, there's really no difference. There might be slight differences on programming, but if you watch the AVR series in my channel, once you get done with that, you will know whatever you need to know to get into pretty much any microcontroller, even if it's an ARM-based microcontroller. My PC struggles with searching the reference manual for the STM. Yeah, but this one only has 16 pages, so there shouldn't be any reason. All right, so let's go ahead and look more at this data sheet. Okay, so you have the supply voltage, and it gives you the minimums, maximums, and typical. And I'm using the 3.3, which is what the STM32 is generally rated at. And the shock limit, this gives you the maximum shock limit that you can apply to this accelerometer. 2000 is already a lot. 1000 is like a car crash or I don't know. It is a serious G load. All right. It'll give you some information on I believe there's settings, the sensitivity. So you can have them in various, if there's noise and you'd want to have it slower than faster, so you can have more samples. But it's essentially telling you the sensitivity of each G. So for every 0.63 volts, you'll have a G difference. So I guess you'd have to take that and divide it by 3.3 volts. So that doesn't sound right, but I think I've already done this in my head before, and it's because I'm live streaming, I'm a little nervous. I'm probably not even thinking straight. Gives you the excitation voltage. I have no idea what this is, and I don't really care what it is, but I'm sure it might be important. The 0G output voltage is the VDD divided by 2. That makes a lot of sense because when I was, actually I'll show you the video. This is a video I just edited today. So you notice that the location of the data was actually around 20, maybe 2100. That equals because it's 0 to 4096. right in between that is about 2000. So that would be the voltage, 3.3 volts divided by 2. So that makes a lot of sense. Frequency response, 6 to 10,000 hertz. So it is a quick accelerometer. You can get a lot of samples per second, up to 10,000 samples per second. How's it going, AJ? Thanks for coming in. Let's see, frequency response is also 15,000. I have no idea what the difference is between these two, but I guess it's noise conditions. So if you have a little bit more noise, then it's more. Yeah, I have to think about that. The resonant frequency is 30,000 minimum hertz, and I did get a lot of ringing, by the way. So that's an interesting aspect. I have a video. Not sure if it was in my last video. The other accelerometer I did for 400 Gs. I may have put it at the end. I'm not really sure, but I did testing of this on an oscilloscope connected very securely to a hammer, and I didn't get the ringing. So mounting recommendations here are extremely important. So I actually thought that the project was going to be a failure until I started reading this, because I'm doing this project with a friend that he needs this for an actual project, which I can't get into, unfortunately. Okay, so full-scale output is plus or minus 1.25. If you multiply that by 2, you're getting close to the 3 volt mark. So your range is a little bit less than the actual 3 volts. So here are the minimums and maximums and typicals for the environmental conditions. So obviously it's going to change with temperature. So you have to take that into account when you're making the program, but I didn't. And in certain contexts you may not need to, and you can also specify whether this needs to be in a specific, if it's a critical situation, like you're in space and you need it to work in within a certain degrees of Celsius, or you'll die, then you'll need to take it into consideration. All right, so a lot of this stuff I don't even look at. Let's see, what are the things that I actually do look at? This is storage information. I don't care about that. So this shows you a block diagram of the internals of it, and this is a piezoelectric sensor. So it has these sensors for each one, for each of the X, Y, and Z outputs, and it uses an amplifier, transistor, and then you have a temperature sensor here. It gives you, if you want to mount this on an SMD, it gives you the temperature profile for actually making it stick to the PCB, melting the solder and things like that. And then you have the thermal shift of the sensitivity. So you have the temperature. If you have high temperature, you're going to have a sensitivity deviation. In contrast, you have with the low temperature, you have a negative sensitivity deviation. So you want to keep it in a certain range, because when things get hot, the metal or whatever that's inside of this is not a MEMS. So a MEMS is actually a metallic structure that is extremely small. You can only see it under a microscope. And a lot of the accelerometers are MEMS. This is a piezoelectric. I don't know how they work, but I'm sure that the physical characteristics may change depending on the temperature of its surroundings. So you have this kind of thing in data sheets. It'll give you guidance on how to mount, and more guidance on mounting. Accelerometer operation at reduced voltages. So it's going to tell you at what voltages is it going to be reliable. So you'll have this, and this is good to know. This is good to understand. but it gives you a pretty good amount of information on each of these. I have no idea. Oh, this is for the temperature sensor. Yeah, which I'm not even using. And temperature sensor stuff, temperature sensor. Okay, so this is the, I was talking about earlier, the voltage divider for the temperature for a thermistor. It's very similar to this. This is just a voltage divider that outputs a voltage for temperature. Let's see, let's take a look at some of the comments. How would you mitigate coding around various environmental conditions? Would you have a separate circuit to capture ambient temps and then have logic account for that? Well, this one has, because temperature seems to be an issue with this accelerometer, like the extreme temperatures, and this accelerometer is very expensive. So it's good that they added a temperature sensor. You could use this temperature sensor in your code and adjust the output, or when you're doing the digital conversion from the analog to digital, and you're using the slope-intercept formula to derive an actual G number, that relates to the G forces. You can use the temperature sensor that's inside to adjust those numbers a little bit according to the graph they've given you. Is it better than the MPU 6050? I don't know what the MPU 6050 is. Let me take a look. Okay, the MPU 6050 it's a three-axis accelerometer, and it also has a gyroscope. This is an IMU generally. It gives you the accelerometer, which is gravity, and it also gives you angular momentum. And it doesn't really give you that much information about it, but okay, so this is for degrees, and it gives you plus or minus 2 Gs, plus or minus 4 Gs, plus or minus 8 Gs, or plus or minus 16 Gs. The one that I'm using here is the accelerometer values are between 25 Gs, which is actually above the maximum that the other one does, and 2000 Gs. This is a very specialized accelerometer for use in high impact scenarios, like I don't know, I can't even think. What do you guys think would be the scenario that this accelerometer would be used in? I'm thinking rocketry, loads, or vibration. You don't even get to those levels of vibration, even like an astronaut being in a seat of a rocket. You don't even get close to that. You probably won't even get close to 25. It's really for maybe accidents, like putting an accelerometer in accident testing, for understanding acceleration in various parts of a car that's being tested, crash tested or something. And that would be, I was able to get values using a hammer, but it took me a pretty good whack to do it. Like a blow that would probably cause a person to get knocked out, if not the worst scenario. 2000 Gs is actually kind of high. Ramshik Val, I hope I'm pronouncing that right. I'm sorry if I'm not. How you doing? Great to you in person, see you in person and live. Loved your micro series back in the days. Thank you so much. I appreciate that. Peter, it has a mass on the piezo sensor that squishes when you accelerate. Very interesting. Okay, that's really cool. So thank you for that. That's good to understand. I think I remember that's how the that's how piezoelectric works. Like the little buzzer I think it has a little diaphragm in there. Okay, as per the question from CNC Timelapse, isn't there temp-based compensation that basically helps it to overcome for the entire range of temp, as well as the temp are also included in IMU-based? Don't actually know. Yeah, I haven't researched this well enough to understand that, but you could. I mean, it depends on the range of the temperature sensor itself, and you can do your own testing and to create your own calibration from temperature ranges. So you could put this in an environment that has extreme temperatures, then hit it, with a known testing rig and understand so you're essentially doing the same testing that they would be doing in-house. But if you wanted to go outside of those temperatures, I guess you'd have to create your own testing rig and simulate your own extreme temperatures. Like if you wanted to go higher than 130 degrees, or you wanted to go lower than negative 60 or negative 55 degrees, you would need to start to look at probably your own testing environment and adjusting your parameters from that. And you can also see that it's curved. So you may not be able to use a linear slope intercept formula to convert these G's, but in simple terms or in simple projects, that might be good enough. You may be close enough to make it work. But if it's a critical application, you'd want to do extensive testing before you even write the code. Okay, pretty much they are already tightly coupled with the ambient temp and biasing purposes, right? So basically this could be done only in case if the manufacturer haven't thought of all the worst case scenarios. Exactly, yeah, that's what I'm talking about. But I mean, 120 degrees Celsius, that's pretty extreme for humans, I think, unless you're using a suit. And then negative 60 degrees in Celsius obviously is the other way. All right, so let's see. How does that go with your idea, CNC, of looking at a data sheet? I know this is very simplistic, and there's a lot more that goes into data sheets, but it has all of the information that you're probably thinking of in order to make this work. So, but in my circumstance, all I did was, I know that this is powered by 3.3 volts. So I went to that part of the data sheet. These are the pins. So I looked at the typical, this is 3.3. I was like, yay, this will work with my microcontroller. I wouldn't need to use some other circuitry to bring it down or bring it up or whatever. But I could also change the range of my reference in the microcontroller so I can match whatever is here. My resolution may not be as good, but I could do that. So then I look at excitation voltage is 3.3 volts. So I'm thinking that well, no, this wouldn't be it right here. So the VDD, okay, so VDD divided by 2, which is, the VDD is right here, 3.3 divided by 2, which would be 1.65. And so that would give me the output voltage at rest. So I would know that I would at least know that. I don't see the minimums and maximums of that, but if it's working with, I was going in just blind. If I know that it's going to be 3.3 volts as the power, generally it's going to be using that range or a lot of that range. And we also looked at the 1.25 was the range, so that could be used. So it would be VDD plus 1.25. Here it is right here, full scale output. So it would be VDD plus 1.25 and VDD minus 1.25. So you can understand the range of voltage you'd be getting out of these pins. Let me show you the pins here. You'd see the range output by pins 1, pins 2, and pins 3. I want to know your this is FZs. I want to know your thought process when choosing communication protocol, how you select it between IC, SPI, etc., and then their implementation. It depends on the device. Some devices will only allow I2C. Now there's an ICCC, SPI, UART, USART. Some devices only allow certain ones, so that would be an easy decision. Like if you need to use a specific device from a specific manufacturer, and they required on that device to use I2C, then use that protocol. If it gives you an option, which I had an accelerometer that gave me the option between I2C and SPI, I go with the one I'm more comfortable with. The output's going to be the same. The communication is going to be the same for its output. So very few specific duration needs to be either calibrated or something to take care. Yeah, in this scenario, I think they've covered the pretty extreme conditions, and who knows what happens outside of those conditions. If the accelerometer fails, it may actually fail and not work anymore. When Peter was talking about the mass with the piezoelectric structure having a mass that changes, that may succumb to the extreme temperatures and succumb in a very bad way. AVR Chief, I am a little late here. What is the live about? You are going to be regularly on this. Yes, I am going to be doing live regular. I'm trying to get into the habit of doing live streams. I'm trying to get over the nervousness of it, and also just wanting to help as much as I can to people that need it. I want to be able to help people coming in that need help with this type of stuff. And I think I enjoy doing live. I'm going to be doing live stuff with the CNC side of things and also the AVR. I'm thinking about doing AVR, or not AVR, ARM and STM probably on Wednesdays, which is today, and probably around 2 o'clock. I have to see if that schedule is good for, I might toy with doing different schedules just to see what kind of response I get. But I'm also going to be doing the CNC stuff, but I think I'm going to be doing that on Fridays and maybe other days as well. So I would like to do at least 2 live streams per week, and I want to do at least 1 video per week. Videos take a long time to edit. Live streams are a little bit easier because I'm not really doing any editing. Editing could take me 5 or 6 hours for a 20-minute video. So it's easier just to interact on a live stream than creating an actual video that in essence saves everybody time, but they don't get the benefit of talking to the creator. And I also do this so I can learn. I'm doing this so I can learn from you guys, and I can, because this is the way I've learned. This is the way I learn, and this is the way I have learned in the past. All the AVR videos that I've created back in 2008 or 2009, I had no idea what I was doing. I did it so I could learn. So doing these videos is just a way for me to expand my own mind. And also, I'm 56, so it's good to keep working that muscle. What kind of topics will you be touching? Because I have a heck load of those. Bring them on. Let me know what those topics are, and if you want to, I have no problem doing collaborations with them. It would be good to know about the project before I go on, because I would probably have to do a little bit of research so I understand the project. But I have no problem helping. Thank you, FZs. CNC, you're doing great. I'm very excited to know that I'll have a live resource to help answer my questions. So cool. You're very welcome. Editing takes me about 20 hours to do a 10-minute video. 20 hours is actually, no. Last night I was doing this video that I made. Your videos are a lot better than mine, so we'll keep it at that. That's why it takes you a lot longer, because of the professionalism is leaps and bounds higher than mine. What I generally do, I'll do a project just like I'm doing it for the first time, and I try to video everything. So the videoing takes a little bit of time. It'll take probably 3 or 4 times longer than the actual project itself. And then editing, because I'm trying to edit a lot of the space, a lot of the when I'm just not saying anything, when I'm trying to think, when I forget to press the pause button, when I forget to unpause, then I have to redo a whole section all over again. But then the editing takes a long time, especially if you add sound, if you add visuals and stuff like that, which I don't do. I try to keep it as raw as possible, but just taking out a lot of the space. But that still takes me a long time. All right, yeah. So I want to. If there's any struggling, it would be cool to know about that. In getting into bare chip microcontrollers, I know my limits. So if I can't if I can't help you, I'll let you know. But it's also, I don't mind going into dialogue about the project maybe because sometimes sounding boards work really well to solve problems in your mind. So maybe you're not thinking of certain things. I have no problem having you on with a live stream and helping you out just as a sounding board. All right, so how long have we been on? And does anybody have any questions? The intention of this video was supposed to do an actual project. It wasn't really talk about this, but I think it's probably good to, this is a good icebreaker. I think it's good to just have an icebreaker to get back into live streaming. Maybe the next live stream we can start a very simple project. Maybe ADC was a little bit too difficult, but definitely watch the video that I'm going to drop today, and you'll see the what I essentially intended to do on the live stream. I wanted to do the actual project if my camera would have worked. This one right here. It was supposed to help showing you the environment and everything. So let's, what would you guys like to see in the next live stream? Since you guys were the first ones here and you guys are the ones the most interested in seeing this live stream, I want to be very action oriented, very into the project on the live streams. I don't want to really just talk about I don't want to talk about myself at all. And answering questions is good, but I want to do things. And if you guys have any suggestions on what you want to see me do, maybe I'll do the ADC in the next one and not drop the video and just have the video in the members section. Let me know what you guys want to see. And then we can do the live stream next time, or I can do the live stream even closer. Maybe on Friday we can do another live stream and do an actual project. How to make an Iron Man suit. Oh my God. That's going into the 3D printing and CNC stuff. The electronics side of things, yeah, that would be pretty fun. Doing the actuation of various parts of the suit or the face or, you know, the mask, the helmet, you know, that could be kind of an interesting idea. All right, so CNC says, I'm all for starting a brand new project and start from scratch. Approach things from this is what I want to make XYZ and work on a project together. Okay, let's do that. That's kind of what I wanted to do today, but I wanted to be guided by you. But maybe it's better just to do it, a project that I'm going to do and want to teach and maybe want to learn better myself. And I can just do the project live and we can talk about it. Wally, thanks for coming in. How do you do a video on how to start a project from scratch to final product? The problem statement, component selection, and documentation, etc. All right, so I'll talk about the vacuum pressure controller that I created. In fact, I had a lot of input from the community on that one. The first thing I'm going to do is look at the microcontroller and search for, let's say, well, let me see if I can find an example. All right, so this is an example of the controller that I designed, and I sell quite a lot of these actually. I've sold these to General Electric, to Virgin Galactic, which was kind of cool. So I've sold these quite a bit, and I've also sold them in interesting scenarios where I developed this for my pick and place machine that I developed a long time ago, and you can see that on my earlier videos. And I needed a way to so I have to come up with a problem. The problem is I have a nozzle. Let's call this the nozzle. So the nozzle has a tip that needs to pick up a component and then move it to another location. So the component needs to be able to stick there. So vacuum is a good way to do it. That's what's used in the industry. So generally you'll have like a little cup or a little tube that picks up the component. So what it needs to do, it needs to have no suction in the beginning, so you're not losing suction in a tank. So you go down, you then start the suction, then you pick it up, you go and place the item, and then you stop the suction. And you actually have to stop the suction and free the you have to free the what do you call it? The tube of suction, because it would still stick to it. So that development took me quite a lot of time, but I was just using a relay and I was just using a vacuum pump and a solenoid valve, and that's all I was using. And the vacuum pump was constantly running. I didn't want it to run all the time. I just wanted to run when I needed it to run. So the problem is, how can I fill up a tank or take air out of a tank and create a vacuum, keep the vacuum, but if the vacuum goes too low when you're sucking up too many components and you're ready for more vacuum in the tank, how do you turn that pump on and then vacuum more air out of that tank, and then when it gets to another threshold, it turns off the pump? So that's what this does. So I have to find a microcontroller that's going to be worthy of doing something like this. The specifications have to be enough that it's going to be able to run a display of some sort, so you can see what the thresholds are. You can see what the vacuum is in inches of mercury. You'd have to have some kind of sensor to sense the vacuum. So I use a sensor by NXP, but it was Freescale at one point. I think they bought them out. That sensor is about $30. It's really expensive. You have to have a way to control the two thresholds. You have to have a way to control, I'm backwards here. You have to have a way to control the contrast for the display. So there's various components that you need to use. Then a relay to turn on and off the vacuum pump itself. And then you have connectors. This one doesn't have the connector on this side, but it would have a connector to power the board, and then it would have a connector for the relay power, or for the switch of the relay, normally open or normally closed. So then you have the components that you need. You could start with just the microcontroller and the sensor, and making sure that the sensor has the values that you require. And this particular one, it was negative 115 kilopascals, and that could be converted to inches of mercury. But that could be used in so many different scenarios. I used it for my pick and place machine, and it had the range from negative 115 kilopascals to 0 pascals is about 0 to 30 inches of mercury, I believe. This is actually a very similar ADC project. It's the sensor provides the voltage outputs for the microcontroller. So then you have once you've done that, you can go ahead and go to the prototyping stage and start to prototype the programming and connecting it to a sensor. Let me see if I can find. Okay, so this is the original board that I developed. This is the prototype. So you can see it's on a perf board. It's got the solder on the bottom there. And this is the relay. This is the initial microcontroller that I actually I teach using this microcontroller on the earlier videos. This was connecting, I think, to the. This is probably power actually, but the sensor is not on this board. I may have needed the sensor for a newer board for my pick and place machine. Who knows? But so then you go to this phase after you do the breadboarding and you've done the programming, and then you're ready. If you know that it's working correctly and it's displaying the correct inches of mercury, you've done your calibration. You know that the sensor is showing you what real world is actually the existing what it is in the real world. Like if you're sucking a certain amount of pressure from the sensor, and you know that pressure, you have like another meter on that line, and then you can make sure that it works. Then you go to the final stage of putting it on a PCB, and then you have another whole slew of problems that you have to solve for, including various grounding requirements for ADC and reducing noise and radio frequency and things like that. So you have to look at the data sheet and the data sheet for the microcontroller for the ADC, and also the data sheet for the sensor has a lot of information about that. So you have to design your PCB in a way that will work effectively and will not have noise output, will not receive noise. It will be able to take the noise away because ADC is very sensitive. In this particular case, you had to actually separate the two ground, the ADC ground and the main ground. And there is I believe there is a connection between them internally on the chip, or I had to make a trace between them, but those kind of things are important. So then you get to that point of creating the PCB, then now your next, well, before that, you also have to look at the economies of scale and how much it's going to cost for the production. Is it going to be, because the size of the board matters, if you're going to have it outsourced, are you going to use, like the sensor in this one was, it's $30. Could I have found a sensor that cost $1? I don't know, but I did try and I couldn't. So it's those kinds of things, decision-making aspects during the development. So that one was a good question. All right, let's see. You should do a poll on your community page with a list of projects and let the community pick. Okay, I can do that. I've done some polls in the past. I think recently I did a poll. So that was doing live stream, what they would like to see, and it was overwhelmingly. I think it was ARM stuff. It was this stuff. So I'm very willing to do that. Okay, so I got your question done, Wally. Any other questions on that, Wally? Okay, Lennon, thank you for coming in. It'll be great if you code everything in bare metal. Yes, that's what I am more familiar with anyway. I'll probably do that unless somebody else wants to see the HAL version of it. There's also CubeMX. Phil's lab does a lot of the CubeMX stuff. So if you want to learn a lot about that, that's a good resource for you. How to use the CMake for automation and things of that nature, but I'm in for any project. The CMake I don't know as much about. I did when I was doing a lot of programming in Linux back in the day, but I've moved away from it because CMake gets very technical and it could scare away a lot of people. What is a gecko wire, Peter? I don't know what that is. Use a trained gecko on a wire. Oh, you mean an actual gecko? All right. All right. So can you detect the resonance modes of a sensor that works with frequency shift through impedance reading with high accuracy? I'm making a piezoelectric MEMS sensor that alternatively used for sensing. I don't know anything about that, but I have no problem taking a look at it and looking at the specifics of it. And maybe in one of these live streams, you can maybe email me some of the stuff, and I can take a look at it and we can talk about it. I am out of breath. I think this was a pretty good. We've been going on for about 2 hours. Unless there's any other questions, I think I'm going to sign off. But I will. What I'll do is I'll put another community post on YouTube. I'll put a few things in there, but if you want to see others, I can also make a different post and add more polls on that. So make sure to look out for my community post on YouTube. Vote for the project that you'd like to see, and suggest in the comments whatever projects that you would like to see that's not on the poll, so I may not be thinking of them all. But some ideas would be ADC, obviously. Outputs. I was talking to CNC Timelapse on the previous live stream about doing connecting a microcontroller to a stepper driver. That would kind of connect the Build Your CNC and STM realms together a little bit. So a lot of the CNC people out there might enjoy watching that as well. And let's see, there's also the communication protocols. There's PWM, there's different ways to react to conditions in the microcontroller, like the DMA mode, the interrupt service routines, those kinds of things. If you haven't watched my interrupt video, watch it. It's where I get beat up in the head by my wife. It was one of my more fun videos, but it maybe I got a concussion out of it. So those are the types of videos I'd probably put in the list. Also the communication protocols like UART, USART, I2C, the SPI. I'm sure there's a lot more that I'm not thinking of, but those types of things. And a PWM is an interesting one, where you can have that works the other way around, like the ADC. It's like digital to analog. It's the digital version of that. So we can talk about that as well. Yeah, let me put the email in both I'll put the email in both YouTube and the Twitch chat. I don't mind making this public. Okay, that looks correct. When you can choose between software and hardware to implement a feature, how do you decide which one to go with? Good question. I will probably always decide on hardware unless it is outside of the cost of the project. Hardware adds another layer of cost to a project. So it's something you need to buy and requires more labor to add it. If in the software case, if it doesn't cause a problem with other peripherals and features that you're using on the microcontroller, then I would always go with the software aspect. An example would be button debouncing, push button debouncing, switch debouncing. So you could create a circuit between the button and the microcontroller that removes that button oscillation, the bounce, because it's the button is a mechanical thing, and because electronics has such a high frequency, you can see all of those little tiny bounces that happen in those two metallic surfaces. Generally, a lot of those push buttons are snap action. So when you press it, you can probably feel a detent or a mechanical change in the metal that causes the button to go down. And that by itself causes a vibration that obviously we can't see with our eyes, but electronics can see very easily. So a hardware versus software approach, you'd have to look at that, because button debouncing in software, some versions can take away a lot of clock cycles. And what do you need in a critical application for, like, let's say you wanted to make a humanoid robot stand up, and that standing is very critical. You don't want, it's not tethered to the ceiling. If the button presses on that a humanoid robot caused a delay inside of the programming, and that stopped the gyroscopic calculations or machine learning or whatever it's using, it could cause that to fail. So you have to look at, there are various software implementations you could use, like the interrupt service routine that takes away, you could take 1,000 clock cycles and turn it into maybe 2 or 3 clock cycles. So there are ways to mitigate that, and you could also introduce hardware. I'm sure in critical applications, hardware might be a better approach, but in most applications for devices around the house and things like that, it's most likely going to be a software implementation to reduce cost. All right, no more questions. Okay, so I'm going to keep the camera running for a little bit, because I hear that YouTube cuts off at the end. So thank you for watching. I appreciate you guys coming in. And come on back if you have questions or want to learn more about microcontrollers and CNC stuff. Hopefully I'll have my cameras working on the next live stream. Thank you so much for coming in.